Ba-da-da, give me that E field for an entire disk of charge. So what we're looking at here is an AP Physics C electricity and magnetism video where we are deriving the electric field for a continuous disk of charge. What this means, continuous, is that this disk we're looking at here on the page, this disk is like filled in. It is continuous everywhere. Okay, there's no holes in it. And it is having some total charge. Let's give it positive Q here. And what we're trying to do here is we're trying to figure out at some point from the disk, and let's go from the center of the disk outward along some Z axis here. If I come out to this point, what is the electric field out here? What would that be? That's what we're going to try to solve in this video. Now, if you haven't seen it yet, go back and watch the electric field for a continuous charge distribution for a ring of charge. You need to watch that video in order to understand this one. And the reason being is all a continuous disk is a series of rings added together. So if we kind of zoom in on the disk right here, we'll see here that we have the disk, and I have here a very thin ring right here in green. Now this ring is some distance little r from the center, from that z-axis, and it is, I guess this should be kind of shaded black here, and it has a tiny infinitesimal thickness given by dr. Okay, so if we actually take a look at this ring here, this, right here, this is some small infinitesimal ring of charge. And if I add up a bunch of rings, I will get the continuous disk. So that's what we're going to try to do here. We're going to add up a infinite amount of infinitely thin rings to build our disk. So the way we can think about this is, let's first just draw a quick go back to what we were talking about with our rings of charges. We learned that for a ring of charge, the electric field is going to equal, and there's a few different ways you could write this if you wanted to, but the one we're going to choose is such that this will be some Z times the actual charge of your ring divided by 4 pi epsilon naught, and then we have this like weird term in the denominator, r squared plus z squared to the 3/2. This is what it was for a ring. Okay. Now, if I'm trying to add up a bunch of different rings, well, I need to think about two things here. Each ring is going to have a different radius, and each ring is going to be built up of a different amount of charge. And that makes sense because, this ring on the inside, it has some smaller radius than a ring on the outside here, which is going to have a larger one. And this ring on the outside, whenever I make this loop, this circle is just straight up larger. So it's going to have more charge sitting on that ring. So these are the two terms I'm going to have to think about expanding into each and every ring. How would you think about it? Well, this term right here is actually pretty easy to think about. It's just going to be some little r, because little r is something that we can integrate over. We can say, hey, look, for each value of r, we can change. Cool. Now, when we think about Q, how do I think about the charge located on this ring here? Well, if I kind of take a look at the shape of the ring, it's kind of like a donut or like a soup label that's been rolled up. If I think about it, if I took this and I snipped it and I unrolled it, it would go from the shape of a circle to the shape of a line. And if I ask myself, well, what's the length of this line? Well, that's just the circumference of a circle, 2 pi r. Now, if this circle had some thickness to it, like this, well, then when I unroll it, I'm going to have a little bit of thickness here like that. And that's going to be some dr component. That's that infinitesimally thickness of the ring there. So if I have a length and a width, I can have an area. And this won't just be an area, this will be an infinitesimal area because I have an infinitesimal thickness to it. So my infinitesimal area will be 2 pi r dr. Now, why does this matter? Well, if we think back to what we've done on our ring and our line of charge example, we were able to say that in those situations, we had a linear charge density. Well, I don't have a linear charge density this time. This is some area. But what I can say is that I have a density of the area. I have a charge density of the area. And there's two ways to write this. Some books will write this as a sigma. Some books will write this as a zeta, whatever. But this is a charge density for a surface area. And that's what we have. It's some surface area here. So what we can say is that if I want to figure out what my charge is, what is my tiny bit of dq on this area, my dq here will simply be the surface charge density times dA. It's my density times my little bit of area, and that gives us sigma, or zeta, whatever you're using, times 2 pi r dr. Now, this is helpful because, as we've seen in prior examples, when I'm trying to add things up, I'm trying to add up a bunch of little dq's here, but I can't add up dq's. What I'm really adding up is some distances here, okay? And luckily I can do this across the ring, because what I'm doing here is I'm saying, look, let's go for each of our smaller rings and concentrically build them out to get the entire setup, okay? So what I'll be able to say here is that now I can say that the electric field given by a thin ring of charge is going to equal, and kind of rewriting what I have up top in this box right here, I can rewrite this as saying Z times, and then my value of Q is going to become sigma times 2 pi r dr, that's all of the positive Q that I had, divided by, and then in my denominator here, I'm going to have the 4 pi epsilon naught again. Nothing's changed there. And then instead of having big R squared, this is going to be some little r squared because it's allowed to change, plus z squared to the 3/2. So I've adjusted my Q into being a more generalized term, and I've adjusted my big R squared into being a more generalized term as well. And this is for a single ring of charge. Now, since I am summing up a bunch of rings here, then what I can say is that, look, this isn't the entire E field. This is a piece of the E field because I have a bunch of rings that I'm adding together. So if I integrate each side here, if I integrate all of my rings, I'm going to get the E field of the continuous disk, which is what I'm looking for. And now I need to integrate my other side here to get that answer. So let's take a look at how to take this integral of the right side, because we've got the setup now. Now we just need to integrate. First thing we'll do is we'll identify all of our constants, which are going to be z, 4 pi, eps naught, the 2, the pi, and the sigma. Those are all constants. I can pull them out. I'm actually not going to pull this 2 out. You're going to see why momentarily. It's going to be a thing where if you're familiar with calculus, you'll see what I did. But I cannot also pull out this z squared because it's added to the r value. So if I go ahead and pull some constants out here, let's see. There's z, there's sigma, there's pi over, here's a 4, here's a pi, here's an eps naught. You know what? Let's get rid of these pi's. Boink, boink, they're gone. And then I'm going to have the integral of 2r dr over the quantity r squared plus z squared to the 3/2 power. Okay? And the cool thing about this is that when we're integrating here, we're integrating from the center of our circle 0 out to the entire radius of this disk. So I'm going from the very center out to the entire radius of the disk. I'm starting here, and I'm going out the radius of the disk all out on the edge. So those are going to be my bounds of my integral. If the reason I didn't take this 2 out here has to do with the way this integral is set up. If you're familiar with calculus, you might see this as a u substitution. What I'm going to have to do is say u is going to equal r squared plus z squared in the denominator. When you take a u substitution, you need to take the derivative of this term, so that du is going to equal 2r dr. Z is a constant, so when I take the derivative of a constant, it's going to be a 0. When you do this, please don't forget to include the dr term. Sometimes students forget that. They just kind of get like sloppy with their calc. The reason why we did that is now I can say that this entire term up here is du, nice, and this term down here is u in my denominator. So what I can do is I can rewrite this as my constants, z sigma 4 eps naught, integral, and some people like to change their bounds I don't like to change my bounds. I like to undo my u's afterwards. Whatever floats your boat calculus-wise. I go 0 to r, and this is going to be du over u to the 3/2 power. I can rewrite this, and I'm just going to keep writing this integral, so I'll just show you how to solve this. I'm going to rewrite this integral as u to the negative 3/2 power. I'm going to bring that up, du. And then from here, when I integrate this, I'm going to add 1 to the exponent and then divide by that new exponent. So it's going to be u to the negative 1/2 power. And when I divide by negative 1/2, I'm going to get a negative 2. Because when you divide by a fraction, it's like multiplying. Okay, so that is what my integral will be. And then I like to switch back from the u, so I'm going to get it's gonna work out like this in the end. It's gonna say z sigma over 4 epsilon naught, my constant, times the quantity of negative 2 over my value of u that I had was r squared plus z squared, and then this is gonna be to the 1/2 power. Okay, and the reason why is, this was a negative, so I moved it into the denominator of the 1/2 power, so there's my 1/2 power, and then the u value I had was r squared plus z squared. So that's what I have here, and then now that I've switched it back into my propers, I can go from 0 to r. Okay, I'm going to do kind of a math trick here, but you don't have to do it like this. I've got this weird negative sitting out in front of the negative 2. If I flip my boundaries, that's going to make this another negative, which is going to make it positive. So I'm going to go 0 and r like that. It's a little math move. I know what's going to happen here from it. I didn't have to do that though. And in doing so, this 2 is a constant, so I'm going to pull it out. So I'm going to have z theta, and then the 2 over 4 is going to become a 2 epsilon naught. So the 2 was here, 2 and 4. And then this is going to be multiplied by 1 over r squared plus z squared, ranging from 0 to r. And I am plugging in these values here for my bounds. I'm plugging them into little r here. Okay, that's the value that I'm integrating across. I'm going out on the disk. So if I do this, keep my constants, z, sigma, 2, epsilon naught, multiplied by, well, this is going to give me 1 over, and then 0 squared plus z squared is just going to be z squared, minus, plugging my value of big R, 1 over r squared plus z squared. Oh, you know what I'm missing here? I'm missing a 1/2. It's sitting right there. I should make sure I carry that down, because this isn't z squared anymore. This is z squared to the 1/2 power, which is just z to the first. Got to make sure you carry those around. That's to the 1/2 power. Okay. What you might be able to notice now is that I'm technically done here, but if I just want to clean things up to make it look book savvy, I could bring this z into both sides. What I'll see here is that I'm going to have sigma over 2 epsilon naught times z over z is 1 minus z over the quantity r squared plus z squared to the 1/2 power. Okay, and that is my final answer there. That's as far as I'm going to go. That is what the electric field due to a continuous disk will look like. The nice thing about this, if you're kind of like thinking about the problem, if you go to an infinite distance away, a very, very far, or rather, if you make the radius of the disk infinite, so it's an infinitely large disk, then what's going to happen is this second term here, this is going to be like z over infinity, and what's going to happen is that's going to essentially be 0. So what you'll find is that the electric field over an infinitely large disk is just going to be equal to this density, charge density, over 2 epsilon naught. It's kind of a cool idea. What you'll also find is that if you make the z value much, much less than r, you'll get the same idea. It will still look like an infinite disk, which just means that, like, you're like very, very close to it, and the disk goes out further than you are up. So both ideas will hold for that right there, which is a kind of cool thing when you think about it. There's a neat way to use this idea to show how the disk will be uniform above it. Anywhere on the disk, if this disk is very, very large, if you're here, it will always look the exact same, the electric field. You can do the same thing for gravity. This derivation here works the exact same for gravity. If you have an infinite disk, gravity will look the same no matter where you are above it. If you're very close or very far, as long as the disk is infinite, you'll get a, just a constant to designate what the E field or the gravitational field will be. Okay. Now, one last thing about this, maybe you're going through this and you're like, you know what, this wasn't that bad of a derivation. I liked finding the electric field for a disk of charge. This wasn't too bad. This isn't the only way that you can find the electric field for a continuous charge distribution on a disk. If you didn't like these integrals, maybe you like derivatives more, we'll see this in a later video, but if you take the potential, which is actually a little easier to find on a continuous disk, if you take the derivative of that potential, that'll actually give you back our answer here. So we'll see this a little bit later on, coming back once again. But for right now, we are finished. I hope you like getting those continuous charge distributions and electric fields from them, from our arcs, our rings, and our continuous disks. The next thing we'll be looking at are voltages or electric potentials for all this stuff as well. But until next time, adios, and y'all take it easy.